E aí também a ideia do projeto é que depois que acabe a palestra, que acabe as aulas, os alunos, os professores possam conversar, tentar organizar algum projeto, alguma parceria, né? Então tem que aproveitar isso também. Não fiquem sem vergonha ou sem medo de falar alguma coisa. Bom? Então, thank you very much for coming here. It's a pleasure to host you here and to speak about. All right. I ask for everyone to ask now about presentation.
Good.
Here and after the
Perfect. All right. Obrigado. Boa tarde, everyone. Greetings. My name is Sam, as I think I heard Paolo mention, and I'm here from the University of Kansas, and I'm going to share some of my research. And I've already met some of you in the classroom setting, but get into a little bit more of the details of what it is that I do and why I'm here. And I don't know how I know Paolo. I met him about 7 or 8 years ago at this point, so I'm really glad to finally have the invitation to visit here and share some of this with all of you. But briefly, kind of what I do is I lead a group at the Kansas Geological Survey, which is part of the University of Kansas, called the HydroEcology of Anthropogenic Landscapes. It's a field at KGS. Oh, thank you. No, it's very nice, thank you. And in general, you know, our group's job is to figure out how different drivers of change affect the water resources of Kansas and the Great Plains region. We have a very kind of basic mission of developing new understanding of hydrological processes and how all that works, and also an applied mission of trying to provide information in a decision capacity that supports people in the region. So broadly, my research kind of fits into 3 themes. There's human-water interactions, primarily in agricultural areas. There's ephemeral hydrology, looking at non-perennial streams and wetlands, and then there's kind of human land and water use decisions and how that affects stream aquifer interactions. And today I'm going to be mostly talking about these 2 categories on the right. There tends to be a lot of overlap among these categories generally. And today's focus is on non-perennial streams. So these are streams that flow part of the year and don't flow other parts of the year. So sometimes they're called intermittent or ephemeral, depending on their exact nature. But they're widespread. The best estimates are that more than half of the global stream network is non-perennial in some way, up to 70% in dry regions. But even in very humid regions like parts of Brazil, there's many, many non-perennial streams. And these are often concentrated in very small watersheds. So they're very short and very kind of locally concentrated, but they add up to make a tremendous proportion of the overall stream network. And they provide many different services that society depends on in some way or the other. And those services can vary depending on if the stream is flowing, dry, or cooled at any given time. So here's an example from a paper by Subington about the different services that we get when the non-perennial streams are flowing, ponded, or dry. So in dry conditions, it allows us to mitigate water scarcity through the infiltration of water into the stream bed. In regulating or flowing conditions, you know, it provides fish and other food sources that people can eat, and many other things in terms of wildlife and human life. But non-perennial streams are widely becoming more common. Estimates in the Great Plains region of the U.S., the central U.S. where I live, is that about 10 kilometers or 9 kilometers a year of perennial streams transition to non-perennial over the past 60 or 70 years. So we're seeing a really widespread expansion of these types of water features, which, of course, will have an implication as far as what are the different services that the hydrologic system in the landscape is providing in these regions. But despite this, most of hydrology is focused historically on perennial river systems. And this is because these river systems are often important in terms of flood mitigation or water supply for cities. Many cities are built around rivers. So most of hydrology, for understandable reasons, is focused on perennial systems. And here we're trying to bring on perennial systems. So today's goal is to talk about 2 different research projects related to flow and change in non-perennial streams. The first one is going to be a very big picture looking across the entire United States about how and why is flow changing in these non-perennial streams. And then the second one is going to be very zoomed in on a very specific stream reach where we've got a lot of long-term monitoring equipment to look at what are the controls and types of tipping points and stability that exist in these non-perennial systems. So the first piece is the continental or national scale analysis across the United States. And really focusing on two questions here. The first is how has stream intermittency changed over the past 40 years? Then the second is what's causing it to change. And this is work that largely emerged from a project that may have some similarity to the CAPS project, in that it's called a research coordination network in the United States, which is meant to bring together researchers working on a topic into kind of a coherent working group type of setting. So this point is led by Dan Allen and Katie Costigan. It's called the Dry Rivers Research Coordination Network. And there's many other collaborators that have been involved in this work. I'm just highlighting a few of the most integral ones here that have contributed to this analysis. So what we did was first we scoured the U.S. Geological Survey stream gauging network for all of the streams that were non-perennial. Of the 10,000 something stream gauges in the United States, only 540 of them are non-perennial and have long-term available data. So it's a very small fraction of the total stream network, despite the fact that, again, these are 50 or upwards of 70% of the total streams in the region. These are kind of colored roughly based on the region that they're in. And as you can see, there's some interesting state-level patterns, these gray outlines of the different states. For example, I'm here in Kansas, over here in the eastern part of the state, where it's quite wet and humid. And our neighbors to the north, Nebraska, don't have any stream gauges on non-perennial streams. This doesn't mean that there's no non-perennial streams in that state. It merely means that the kind of hydrologic monitoring investments in that area have not been focused on non-perennial streams. And you can see there's generally much more gauging of non-perennial streams kind of the south and the western part of the United States, where it tends to be hotter than most of it. So with these hydrologic gauging stations, we extracted hydrologic signatures from each of these, describing the duration, rate, and timing of no-flow conditions. So if you imagine a hydrograph for a given year, where stream flows on our y-axis and then the day of the year is on our x-axis, we took out three things. To quantify the duration, we extracted the annual number of no-flow days, so the number of days that discharge is equal to 0. To calculate the rate of drying, we took the number of days from the peak in the stream flow to when it reached 0. So we were rapidly drying river would have a shorter duration, or a shorter rate here, slower, kind of more receding river would have a longer duration. And then to figure out the timing of no-flow conditions in the year, we extracted the day of the first no-flow in the year. And we did this annually for a 38-year period, from 1980 to 2018, when we had data available for all types of species. What we could then do is try a number of different approaches to evaluate what are the different types of change and drivers of change. And fundamentally, to look at the where there was significant change in any of these hydrologic signatures, we used a man-Kendall trend test, which is a test that simply tells you kind of, is it increasing, is it decreasing, or is it staying relatively stable? And then to evaluate what the drivers are of these change, we used random forest models that were kind of trying to relate these hydrologic signatures to a number of different covariates. And here are a number of maps that appear a bit small on here, but hopefully all you really need to see is that there's kind of a big red splotch in kind of the southern and western portions of the domain. So this here is the results of the Kendall Tau, so the man-Kendall trend test, where any red point is showing a drying trend in the duration of no flow. In other words, there's going to be more dry days in each year. Any blue point, of which there's not very many, are showing a place where there's a wetting trend, where there's more no-flow days, fewer no-flow days in a given year. And we can see overall that 40% of the gauge network in this region had a significant trend in one direction or the other. About 26% was drying, 15% wetting, with the drying most dominant kind of the southern and the western United States, where it tends to be more arid. If we look at our other two signatures, these again are showing drying trends in red and wetting trends in blue. Here we've got the rate, the days of each no-flow, and here we've got the timing of the first no-flow day. We can see that there's significant trends in both these as well. For the rate, there's trends in 15% of gauges, and for the timing, there's trends in 14% of gauges. And overall, if you look at these 540 gauges, 50% of them have a significant trend in at least one of these stream networks. So of that, 50% of the United States stream network, it's not perennial, half of those are exhibiting a significant change in some combination of the rate, duration, and timing of snowfall conditions. So this is suggesting that there's very kind of profound and widespread change in non-perennial systems that tends to be fairly undercharacterized due to the lack of monitoring in these settings. If you look at how those trends break down in terms of different regions in the United States, we're now showing that for each of these on the y-axis is that single pal, once again, for the direction of the trend. Blue being wetter, so a positive number being wetter here and here, the negative number being wetter here, red being drier. And these are broken down into the 6 regions. We've got eastern forests, Mediterranean, California, the northern and southern Great Plains, western deserts, and western mountains. And you can see that in general, there's some very strong regional patterns for the trends in duration and time. We've got significant distributions of drying in the southern United States, in particular, kind of up here in Mediterranean, California, and the southern Great Plains, western deserts. All of these regions are exhibiting kind of above average or a disproportionate amount of drying trends. And wetting in the northern United States, in particular, the northern Great Plains region. There's no real pattern in the rate of drying change. So these ones here generally are all kind of along that zero line and distributed somewhat more like across that zero line. So this suggests that the drying and, the duration and the timing tend to have some regional characteristic drivers, while the rate is more spatially distributed somewhat standard. If you look, now we're doing that same thing. We've got our trend on the x-axis now, and we've been these into different latitude bands, and you can see that same message. If you look up in the northern part, for instance, we've got significant wetting trend over on this side and wetting trend over here as well. And as you move from north to south in the United States, you go up to kind of a wetting good characteristic pattern. So, to get at the first question, how has human changed over the past 40 years? Well, what we can see is that half the gauges are exhibiting significant change, with trends in duration, or the number of no-flow days in each year, being the most widespread. What this means, how this kind of manifests, is there were more drying trends than wetting trends, and the drying was predominantly located in the south, where there were more non-perennial stream gauges. So if you took a continent-wide perspective and had your gauges distributed somewhat equally, there may be comparable amounts of drying and wetting trends. You just don't necessarily have the spatial resolution of data to be able to characterize that. And there tends to be less coherence in the trend for the rate of drying compared to either the duration or the timing. So this picture, there's widespread change in the system. And then the second question, of course, is why? So what are the drivers of the spatial and temporal variability between the regions? Well, to get at this, we use the random forest, which is a type of statistical modeling approach that allows for multiple predictors, nonlinear relationships. You don't have as large of a risk of overfitting in some approaches, but basically it builds decision trees to try to classify, for a given output. In this case, you're trying to predict each hydrologic signature for each year. It builds a decision tree based on a number of different covariates that you get as predictors. And the covariates that we're providing included climatic information, land use information, physiographic information like slope, elevation range, that sort of thing. So if you build these models, you can look at how well they perform. Here we're showing the observed versus predicted for each of these 3 metrics, our duration, our rate, and our timing. On the top, we've got our training sample for the model, and on our bottom, we've got our testing sample for the model. And overall, we used an 80-20 split. In general, we had a less than 15% normalized statistical error for all of these different metrics, with the best predictions of no-flow duration and the worst predictions of no-flow rate. And this kind of makes sense intuitively because, as we saw, there's much more predictable patterns in changes in no-flow duration than there are in the no-flow rate. And the value of these random forest models, now that we've got them trained and at least somewhat reasonably well performing, we can use them to extract the predictors or covariates that we think are most influential on these changes in no-flow conditions. So, what we've got here is a variable importance indicator on the x-axis, and then different specific variables on the y-axis. And the specific variables aren't of great interest, but what isn't of interest is the category. And that category is denoted as the color line. So any red line here indicates that it's a climatic variable. Any green line indicates it's either related to land or water use, and any blue line indicates that it's a physiographic variable. And the higher up it is on here, the more important it is. So we can see that trends or changes in interannual variability in the no-flow duration tend to be controlled by a mixture of climatic, or red, and physiographic, or blue, properties on here. If you look at the rate and the timing of no-flow conditions, that story changes a little bit. The rate, which again was our hardest one to predict, seems to be the most strongly influenced by land use and physiology, things that don't vary as dynamically from year to year as climatic variables. In particular, natural land cover was very important to the rate of drawdown. These important variables here are wetland area, forest area, and grass area. So it seems to be representing to some extent which the landscape will be modified. The timing, on the other hand, is almost entirely controlled by climate. So the ratio of precipitation to potential evapotranspiration in the preceding year is the dominant predictor there. And in general, the antecedent conditions are really favorable to. So the second piece, what are the drivers? Well, the drivers tend to be provided by the ceramic forest model, which did a reasonably good job of predicting. And in general, the hydrologic signatures have different ranks in the the duration tends to be the most strongly predicted by climate and geography, while the rate tends to be by land use and geography. And timing is really ultimately controlled by climate and the prior year. So at the continental scale, what it seems like is in areas where there's an aridifying trend, there's aridifying climatic trend, like the southern and western portions of the United States. We're similar to seeing a strong kind of aridifying trend in the stream system or the hydrological system. We're seeing these significant reductions in flow presence. If we zoom in on Kansas, which is the best state in the United States, and has a very unique characteristic in that it is strongly stratified in terms of precipitation, with very dry western portion of the state and a relatively wet eastern portion of the state. Again, I live right around here, the more so in the wetter part of the state. This gray shading in the background is the High Plains Aquifer, which is a heavily used aquifer for irrigation, supports some billions of dollars of economic output every year. And this map is showing the stream network. Any line on here that is blue is a perennial stream, has been and still is. Any line on here that's red, and you can see many of these overlying into the origination of the High Plains Aquifer, was perennial in the 1960s, so before kind of the expansion of groundwater pumping. But as of 2009, transitioned to a non-perennial forestry. And what you can see is over the western kind of third of the state, most of the stream network is shifted from perennial to arid. And the site we're going to zoom in on here is the Kansas River near Monterey, Kansas. So it's kind of right at this transition point, where to the west of it, things have by and large shifted to non-perennial flow regimes. And to the east of it, you still have perennial flow regimes as you go a bit downstream, because you're getting into wetter conditions over here. So here's two examples of what the river system looks like in its dry and wet conditions. You see in the dry conditions, it's just a big sandy riverbed, and you can go out there and wander around. People like to have bonfires down there and just hang out. In the wet conditions, it can be very, flooded, can't walk around, can't do much of anything. There used to be beavers that lived here before it switched from a perennial to non-perennial flow regime. So as you can see, there's two very distinct hydrologic states where that's apparent. If you think about what the subsurface looks like, kind of beneath what we can see here, there's three primary hydrostratigraphic units. Near the surface, this kind of sandy area that these individuals are standing on is an alluvial aquifer. And an alluvial aquifer is coarse, really coarse standing gravel with silty clay. So you dump a bucket of water and it's going right away. Unbelievably conductive. That's about 10 meters thick. Beneath that is an extremely low permeability clay confinement layer. And this layer is kind of a mystery that we're working on unraveling. If you do a hydraulic test in that clay layer, you'll see that it's extraordinarily low permeability. Like if you pull some water out of the well, it'll take months for the water in that well to recover. But there's evidence that I'll show soon that water moves through that clay layer. So we're suspecting that there's some leaky portions of it, maybe where the layer thins out, or there's a crack in the layer, or perhaps going around the annual casing of our well, we've introduced leaks in it. So there's this weird clay layer that is kind of separating the alluvial aquifer and the High Plains Aquifer. And this High Plains Aquifer, again, is a really highly productive standing gravel aquifer with lots of pumping for primarily agricultural purposes. If you look at the stream flow record, this is one that students in the course have seen a few times, you'll see that it's a very not linear drying trend. So this is a plot showing mean daily discharge from 1998 up to the end of 2021. It's log scale. Everything that's shaded yellow on here is a period of no flow, zero flow. And you can see that it's, while kind of in the previous continental scale stuff, we're just figuring out changes or trends in the hydrology of non-perennial streams. We see here, when we zoom in on this one specific site, that it's extremely nonlinear. We've got multi-year shifts between, our wet or flowing conditions and our dry or no flowing conditions that are only occasionally interrupted with very discounted flow events. So, we've got periods ranging from, a single couple days of flow within a 4-year period. And then, that's kind of counterbalanced by another 4-year period or something like that. So the questions we're investigating here were, number one, do wet and dry conditions show any evidence of stability in either of these two states? And number two, if so, what are the feedback and interactions that create stability in this system? And I'll highlight the co-authors that involved in this, two students that we're working with, like the Prof and Palestra, as well as some colleagues at Keyshain, Aaron Siebold, who's also at the KGS, and one of my Shane collaborators on a lot of projects. So our hypothesis, based on looking at that stream flow hydrograph, was that this system is exhibiting alternative stable states. And if you encountered alternative stable states in other literature, like ecological literature that's quite common, these are system configurations that are caused by negative feedback that create basins of attraction. So if you imagine this kind of ball representing the hydrological system at a given time, and this sort of kind of stability landscape, what it means is that once you get sort of trapped in one of the states, the dry state for instance, it can be very hard to get enough kind of inertia to move past the tipping point and get into the wet state. So once you're in a configuration, it's hard to move to another configuration. And while it's challenging or impossible to definitively prove stability using observational data alone, there are many different hints we can extract from environmental climate series data. Three of them that we're going to investigate here are whether you've got jumps in the time series data, a multimodal distribution of your variable interest, and multiple or hysteretic relationships between the variable you're interested in and then the controlling time series. So in this case, we're just going to examine each of those three potential instances and see if we've got evidence for those. First, if we look at jumps in the time series data. So this is what we've done to summarize the number of no flow days in each month as a percentage. So 0 value would indicate it was flowing the entire month, 100 value would indicate it was dry the entire month. And these red and blue shadings are corresponding to 5 different hydrologic regimes we identified with statistical radiation shading. What we can see is that there's very kind of abrupt and rapid jumps between the 0% and the 5%, or sorry, 0% and 100% emissions. These are alternating wet-dry regimes that have very rapid onset and offset. If you look at potential driver variables, so here we've got precipitation plotted through time, and here we've got the annual water use in the area kind of surrounding the site plotted through time. You can see that there's not really any accompanying zone. We might be able to kind of convince ourselves that, before this wet-dry regime shift, there was an increasing trend in groundwater pumping or something like that. But there's definitely nothing that looks like that top panel in either of these, in either the middle or the bottom panel, that would be corresponding to that abrupt shift in the hydrologic system. If we think about our second thing, looking for multimodal distribution, what I've done is taken the data from that last graph and put it into the histogram here. And you can see that almost all of the flow conditions are either on the far left side, meaning between 0 and 10% of the month with no flow, or on the far right side, meaning between 90 and 100% of the month with no flow. And in general, this happens in 254 of the 276 months that we observed. So well over 90% of the month is either at one of these extremes or the other. And really, you can barely even see the ones that are in the intermediate section. So we've got a highly multimodal flow distribution. If we look at precipitation and pumping, once again, it's potential explanatory variables. since these are not parallel. We've got a unimodal and right-skewed distribution of precipitation. If you look at the monthly time series, if you look at the annual pumping, we have monthly data for pumping, but if you look at the annual, there's also a unimodal from a model. So again, the hydrologic state variable is not matching any of our potential driver variables. If we look at our final clue or hint of interest, what we're looking for is hysteresis in the relationship between the stream intermittency and the potential drivers. So hysteresis, in other words, means that the response of the system to a change of some sort will depend on where it is in that system space. So in this plot, we're now plotting again on our y-axis the no-flow days as a percentage of each month. And our x-axis is a climatic index called the SPEI. Over here on the left side, this means meteorologically drier. Over here on the right side, it's meteorologically wetter. And the points are kind of connected to time and color based on the water that you're in. So in general, what we see is kind of start from the earliest time here. We go over to the left, we loop around like this, we go around up here, and then come back down. We've got a nice hysteresis loop here. And this is how we kind of move through that camera space. As you're kind of moving from right to left, from the start of our period when the stream is flowing to the left, we've got 0% no flow days, so the stream is flowing the entire time, and moving from wetter than average to drier than average conditions. Once you reach some threshold of about -1, it looks like, in SPEI, then there's a very rapid transition from 0% to 100% cleanup. So the stream goes from completely wet to completely dry. Once you get up to the top here, from that 100% zone, the stream, wiggles around a little bit, but it has to go this way, all the way out to about a +1 SPEI, in order to transition from completely dry back to completely wet. In other words, when it hits this 0 point of average conditions, average environmental conditions, returning to normal climate doesn't return it to its normal flow regime before finally it wets down. So what does this mean as far as our question? Do we see evidence for stability? Well, yes, all three of those hints that we investigated showed strong empirical evidence for potential stable states, wet and dry stable states in this system. So that was encouraging. Again, we can't prove it, but this seems to be a pretty clear picture where all of the lines we looked at suggested there's stability in the system. So in order to really convince ourselves of this, we have to figure out why. What are the feedbacks, what are the interactions that can create these spaces of attraction in primary space? So really the key is stream aquifer interaction. This is a time series now showing water level in 3 different parts of the hydrologic system. This purplish line is in the river, this orange line is in the alluvial aquifer, and this red line is in the high plains aquifer, so underneath that confinement layer. The purple line disappears during the dry period because there's no water in the river. And this kind of seasonal reduction and increase in the high plains aquifer is the signal pump. So when people pump in the summer months, water levels go down and they recover in the winter months when people finish pump off. And what we can see is that the wet and dry regime is controlled almost completely by aquifer water levels in the alluvial aquifer for the storage of the system. If we look, for example, in this zone here, where we've got a wet regime that's happening at this time period, we've got an upward pedal gradient. So the water levels are highest in the confined aquifer, intermediate in the alluvial aquifer, and lowest in the river. In other words, water is flowing from the aquifer system into the river, supporting the stream in the system. In contrast, look at the dry period. We've got a gradient from the stream when there's on the rare occasions there is water in the stream, down into the alluvial aquifer and into the high plains aquifer. So there's a really kind of sharp, losing system in that condition. And you can really see how these different climatic influences, climatic and human influences, can drive this system by reversing that stream aquifer gradient. For instance, this wet dry condition right here, you can see there's a very kind of positive and happy kind of gaming system right up until the onset of pumping in the summer. Then that drops the high plains aquifer water levels very rapidly. That in turn drops the alluvial aquifer levels, which follow closely behind. And then the river dries up. And without that sort of recharge from the river, these water levels are not able to recover in the other years. So we try to put this into conceptual space. What are the feedbacks and interactions that create stability? Well, our aquifer started in the wet condition in 1998 when our stream flow data started. So when you're in this wet condition, you've got sustained flow. If you've got sustained flow, that means water can move through the river network, making its way down the river corridor without seeping into the stream. You don't see those transmission losses. That means that more water makes it to the site, allowing for recharge into alluvial and high conduct during high flow events, which in turn supports the water table above the stream bed. In other words, you have this kind of feedback in the system that helps sustain water levels above the stream bed elevation, sustain flow within the stream. If you get some sort of a shock that can induce a regime shift, and this is based on the evidence, I talked about pumping, but there's also reducing inflows from upstream due to upstream surface water diversion, and or severe drought, strong drought climate conditions. That can basically push that ball from the wet state into the dry state. And once you're in the dry state, you've got very infrequent inflows in the system, so there's very little recharge possible. When there is water there, there's very high vegetation and pumping water use, so the water leaves the system more rapidly. And that in turn keeps the water table above the stream bed, maintaining no flow state, which again, you're stuck in this feedback loop. It's kind of holding you in that dry state. Until you get one of these rare events like the large inflow from upstream or flowing water climate conditions that kind of push you back one or the other. So this, we think, is the stabilizing feedback loop that's creating those stability states. There's kind of local drivers from stream aquifer interaction, recharge of the soil column, as well as more broader regional processes. Inflows from upstream, water use, there's some evidence that construction of a reservoir upstream has perhaps been one of the regional processes that's been a major alteration of upstream flows. So, if we take these two pieces of the puzzle, the continental scale stuff and then the scale stuff, what are the general conclusions we draw about non-perennial streams, how they're functioning and how they're changing over time? Well, first, you can see there can be very long time lags in non-perennial stream flow. So year-plus time lag between when something changes, whether that's climate or human activity or something like that, and when the stream system fully responds. And this is in kind of contrast to a common perspective of non-perennial and ephemeral streams where, they flow when it rains and then they stop. So we can see that there's very long periods of kind of hydrologic memory in the system. Second, we see the physiographic characteristics. So the site-specific characteristics like flow, aquifer, etc., provide a template on which climate and human activities, which are much more dynamic, are able to interact. So these time scales of influence that precipitation, climate, human activities hold over the system can change based on antecedent conditions. That's kind of the core of this hysteretic process that we saw. And, as I noted earlier, we've got a very sparse monitoring network for non-perennial streams. Even, with USGS, which is one of the world's best monitoring systems, there's still very little monitoring in non-perennial streams. And where there is monitoring in non-perennial streams, there's almost never monitoring close to surface and the subsurface. So this one site we've got in Kansas is kind of an anomaly in terms of the fact that USGS is working there, and the KGS kind of investing resources to that subsurface monitoring. So these surface-subsurface feedbacks are really not well understood. But in turn, the stability that we observed and the fact that we've got these stable states suggests that there's going to be very difficult shifts back to perennial flow regimes for all of these perennial streams that are moving across the U.S. Once they kind of move into this dry state, like we saw in much of the southern and western United States, it'll be very challenging for them to shift back into a wetter flowing state because of these stabilizing effects that we observed on this site. So that's a bummer. What do we do about it? Well, we're working on a number of different projects kind of going forward. So the first one, and this is kind of a watershed-focused project called AIM, Aquatic Salinity Effects on Microbiome Streams, is focused on integrating the hydrological piece of this puzzle with other drivers of water quality, so biogeochemistry and microbial ecology. We've got a big kind of paired 9 watershed design spanning the entire U.S. We're going out and monitoring really small, kind of underrepresented stream systems to try to figure out with paired biogeochemical sampling and phase data and microbial collection, how do these different pieces of the puzzle come together? Is hydrology a driver that forces the other two, or are the biochemistry and microbial system in some way controlling or feeding back on the hydrological system? Second, and I think this is really where there's a lot of potential, is bridging across functions. We've done this one study with our Kansas Geological Survey in Larned to look at tipping points and drivers of change in these systems. Similarly, work by Tim Peterson in Australia has found some really fascinating transitions in the stream flow regime in response to the millennium drought. So in Australia, around the turn of the millennium, there was a multi-year prolonged drought. And something like 40% of the streams in Australia, even now that climate is returned to normal, have never recovered their pre-drought stream flow regime. So there's some type of tipping behavior that's going on there. What it's caused by? We don't know. Brazil, I think, has a unique data set, a copper data set, that would be really useful to try to dig into some of these questions. Looking for perennial and non-perennial shifts from, kind of persistently high to persistently low conditions, whether that's in response to land use change, there's a few drought in kind of 2015, 2017 period, other kind of floods, compound stressors. I think there's a ton of potential for exploring there. And in particular, we're going to figure out some way to couple the groundwater and stream flow. And the piece that I didn't get into in this presentation, but I think would be really fascinating, is the atmospheric moisture recycling. So as land use change affects the flux of water from the land surface up into the atmosphere, what does that mean for precipitation events at the broader regional scale? And how can that further kind of reinforce or dampen the stabilizing feedback conveyed through the practice? So that's what I've got for today. Thank you all for being here and paying attention. I will highlight, I'm recruiting a postdoc and major master's student, so if you know anybody that would be interested in these types of roles, I'd be happy to talk with them while I'm here and just share more about the details. So, thanks. Yeah, good question. So we didn't have a good groundwater withdrawal data set that we could put in there. We tried to get at the groundwater in a few other ways based on the irrigated land cover and the cropland cover in the surrounding areas, but that doesn't give us, the true groundwater extraction volume. So I think that's something that if we're able to kind of put that, kind of connect that piece to the trends a little bit more clearly, I think would be very valuable. Because I know I kind of mentioned on the last slide compound stressors, and I think I want to emphasize the fact that drier climatic conditions are a compound stressor on streams because of not just the lack of water that's falling from the sky to get into the stream, but also the fact that any irrigator has to increase their irrigation volumes in response to those drier conditions. So the streams are kind of losing water both from above and from below in those dry conditions. So I think that would be a cool thing to figure out how to do.
I think maybe it would help with something like the relativity concept or
yeah.
Or other kind of
Yeah. It would be great to have an index where, you can kind of look at it against some of these hydrologic signatures like filtration or something like that, and really kind of see when there's that non-linear transition between the two. If you have tipping point behavior and experiencing a linear change in hydrologic disturbance or something like that, then what you would expect is that at some threshold value of hydrologic disturbance, you would exhibit your hydrologic system would have a nonlinear change. And trying to figure out what is that threshold value and how does it vary across space and across time would really be key to help survey kind of our mentioning and figure out, okay, what's value and where are places that are approaching that value and where can we kind of anticipate and try to mediate some of these changes that might happen.
With hydrological and hydrological very important to understand environmental indicators. It's very nice and very important. Have you tried to correlate land use with groundwater flotation and tectonic behavior of that?
Good question. I have not looked into the tectonic side of things at all. I'd be curious to hear more what you might expect to see there. That's never even crossed my mind, but I love the idea. We've looked a little bit at kind of the groundwater and the agricultural lens, primarily from the perspective of groundwater conservation in Kansas. In many of these regions, across the region generally, there's been really kind of extensive use of the groundwater resource that exceeds the rate at which it's recharged to replenish. So, big decline of the historical period. And that creates another kind of opportunity for hysteresis because in areas without this aquifer, where you've just got kind of the stream flowing over the landscape and the high plains aquifer underneath, once the water table drops by just a few meters, then it's below the stream bed and the stream's dry. But if it continues to drop time after time after time, it doesn't necessarily have any effect on the stream today, but it has a strong effect on the ability of the stream to recover. And I think one area in which Kansas is maybe fortunate relative to places like California is that we have very little clay in the aquifer, so there's not much compression or subsidence when the water table does draw down, which means a lot of that storage is recoverable. But there's no action towards recovering it right now. So I don't know if that got your question at all, but I'd love to talk more about the tectonic piece, because that's something I'm
Yeah, because for years, it seems to many years that it's good time, but
Yeah, point to that.
we have to see in other stages of the environment.
Yeah, that's a great point. And over, I was at a talk somewhat recently by a geomorphologist, a paleogeomorphologist, and he was talking about how, kind of in the period where the aquifer was being deposited, it was a very wet climatic condition because it was transporting all of the sediment from the Rocky Mountains, the very, gravel and sand type stuff, all the way down there. There's enormous rivers, hundreds of meters wide in their size. Which is, it's hard to imagine today.
When you complete your first project, do you try to continue in different times that you can, for example, 10 years, 5 years, and then you graduate
Yeah, that's a great idea. We didn't do that specifically. We did try lots of different trend identification approaches. What's challenging about it, a common hydrologic trend approach is send slope, which is if you take all the points, you calculate the slope between every set of pairs and take a median of those. And that's challenging when you have more than half of your data, either as zeros or 100s, because then you end up with a slope of 0 because all those pairs are zeros. So the actual identification of an appropriate metric for calculating that slope was a real challenge. And I think that trying to investigate the broader non-linear characteristics of the slope is something that actually a student with Chipping is working on. And he's kind of taking this data set and trying to figure out with breakpoint detection techniques when in time do we see breakpoints, and do those breakpoints, the non-linearities, vary in some coherent manner. Like, is there kind of a regional transition in the high plains in the 1980s, for instance, in one direction or the other?
What is open water, or?
I think it's, I think that for much of this, much where I live, I think it's pumping water. And it'll specifically when the pumping kind of exceeded the recharge rate, for a handful of years, long enough to drop the water table below the streambed elevation. But I think in places like Arizona and California, it's probably not the pumping story. It's probably going to be more of a climatic shift and some balance between precipitation and evapotranspiration. And there may, in those areas it may be much more linear, because it really is just kind of responsive to precipitation in and of itself.
Something makes a difference between hurricanes and emerald streams, the days and the
Yeah.
Some say that emerald streams only receive water from direct runoff, and so does that very conclusion from the water.
Yeah, so a colleague of mine did a literature review of kind of the terminology around non-perennial streams. So things like intermittent, ephemeral, non-perennial, variably inundated, all these different terms. I found that largely there was not consistency in the definition, which is why I try to use non-perennial streams. It's kind of a cover-all that encompasses them all. But in general, kind of the way I was trained and the way that I've always thought about it is similar to what you were saying. So ephemeral stream will only flow in rain. And an intermittent stream has some, probably seasonal connection to the groundwater system. So there's periods of time where it's staying flow and periods of time where there's no flow. And what's interesting about, this river in particular, our Kansas River, is we saw there was periods where it could be defined as perennial or even intermittent because there was that sustained connection with the groundwater system. And there was also periods where it could be considered ephemeral because the water table dropped below and then it'll just float over rain. So I think the static classification for, these types of rivers is challenging from a terminology perspective. But it's really critical. In the U.S., there's a lot of rule and policy debate right now, specifically around ephemeral systems. And the Supreme Court of the United States has said these non-perennial systems have to be treated and managed for the benefit of the broader hydrologic system if there's a significant nexus. That's exactly what it is, a significant nexus between them and the downstream waters they support. And that significant nexus is all about the connectivity between upstream and downstream. And everyone is kind of trying to grapple with how do we define that? What does it mean? Does it mean intermittent but not ephemeral? Does it mean ephemeral but sometimes? So it's a big, open question of when we say significant connections, what do we mean? And what types of systems have these significant connections?
Maybe more a little bit for dental food, how long is the water test that you were using, and for how many times per month?
Yeah, absolutely. So kind of the two field sites that I have the most at is this one. This is a long-term geological survey field project. And you can't see it, but we've got about 19 different monitoring wells kind of spread across the floodplain here. And this one's great because it's very just sensor-driven. So we just set the sensors out there, we come back every 12 months and download them and keep them going. This project, the AIMS project, where we've got these 9 watersheds spread across the country, is the opposite. It's very intensive. Our students have actually been out there every day this week because it's their spring break. So they've been putting in these sensors. They burn some of these watersheds for cattle grazing. So we've got to take the sensors out when they're going to burn and put them back in so they don't get melted.
And how will you use
These ones, this one pictured here is one of the most scenic ones. It's about 3 hours from the university. Yeah. Yeah, drive. You know, if it's a multi-day thing, we'll stay overnight. Like we can camp. We can camp there. But it's full of cows, and the ranchers don't like us camping there very much. So we try to avoid. It's very much like a people challenge, not a landscape challenge. But yeah, for the water quality sensors in particular, it's very kind of high frequency water quality sensors. They need to be visited every 3 weeks for maintenance. So, you know, for a 5-year period, we can go out there every 3 weeks, you know, during the time.
And do you have someone specifically part of the job?
A PhD student, or a handful of PhD students. Yeah. This project is a very large, multi-state, multi-institution project. So in each of the there's sort of a mountainous region where we've got 3 watersheds, the Great Plains where we've got 3 watersheds, and then the southeast where we've got 3 watersheds. In each one of those regions, there's, you know, about a postdoc, a technician, and 2 or 3 graduate students that are all sort of doing that role. And each student sort of has their own area of specialty. Kind of the students that I'm working with are mostly working on putting out these stream intermittency sensors that are able to characterize when is it flowing and when is it not. I'm trying to distribute, you know, over 100 of them around the watershed to figure out these really fun scale patterns. Yeah. But yeah, I don't know. You gotta like going outside for this project. The projects I'm recruiting right now are not that field heavy. They're much more nuanced. Don't get scared about it. Good. Thanks everyone for being here.